In this segment, I'd like to deal with sort of a big picture of computer science, and um, sort of I divide that space into two very broad areas. One being sort of the pieces that we deal with, and then the other is how do we actually solve problems with those pieces. Um, And so you have to understand the pieces in order to put them together to solve the puzzles. The nice thing about computer science is there are a lot of pieces that we have to solve problems, but it also has the ability that you can make your own pieces out of smaller pieces to address problems. So it's sort of this thing that continues to build on itself, and quite frankly, that's what's enabled us to have a lot of the advancements we have enjoy today in computer science. So let me sort of draw this line down the middle here, um, and in this class, some of the difficulty is you have to learn the pieces and how to use them at the same time. And so let me give you some framework here. In terms of the pieces, in general, um, there we will deal with variables. We will deal with statements. We will deal with functions. We will deal with a concept known as iteration, and conditionals. Those are sort of the five major areas. There are many sub areas under that. Just to give you an idea, variables are names that we give memory spaces. Um, Statements are just simply statements that or instructions that we give the computer to execute. Functions are bundles of those statements, which allow us to reuse certain pieces of code and reuse groups of statements. Iterations allow us to do things over and over, which computers are very, very good at. A computer doing something a million times is very trivial, as opposed to a human, and so that's where computers are very helpful. And then conditionals are how we make computers make decisions. And they aren't decisions like you and I make on a daily basis, but they usually boil down to either true or false decisions. And if you arrange true or false decisions in the proper way, you can get some very good and effective results. On the other side, in solving the problems, I like to think of a six-stage process, and I sort of got this process from teaching this class in various forms over the years, and I got it from data documents that we used to use to program in Scheme, the design documents that we used to use. And so the first thing you have to do is you have to read the problem, and identify what you've been given and what solution is required. So that's sort of step one. Step two would be to come up with a solution or an algorithm. So derive an algorithm. An algorithm is nothing more than a way to solve a problem. And so deriving an algorithm, think through how are you going to solve the problem. Do some test cases to see if your algorithm works. So do this, you can jot it down in the back of an envelope. You just need to, you can draw pictures. However you do it, figure out how you're going to solve the problem, how you're going to get from your givens to your desired solution. Step three, after you've derived your algorithm, I think it's very good to articulate your algorithm. And you could do it with flow charts, you could do narratives, but basically imagine if you have to describe your solution step by step to a fourth grader or a fifth grader, and break it down into basic steps that follow each other, that are logical and lead you to your solution. And so if you can get to the part where you can articulate your algorithm, you have it, you can write it down in sentences, you can draw pictures, you can draw a flow chart, you can explain to somebody how you're going about solving the problem. Now you're ready for step 4. Notice that steps 1 through 3, I've yet to touch a computer or write some code. It is all about figuring out the solution. Once you get the solution, you enter step 4, which is you translate your solution into a computer language. Because you were trying to get a computer to solve it, you must translate it into a computer language. So now you've articulated your algorithm to a fifth grader. Now you've got to articulate it into code or to a computer, which is much more rigid than a human being. So translating it into code, this is programming. This is where the actual programming begins, in terms of what most people think about programming. But really, it really starts up here at step 1. So our particular language that we're going to translate into in this course is MATLAB. And so translate it into code. Then once you've translated it into code, then you have to test it. And so you have to test to see if it's right. And if you've done your work right, you thought of your test when you derived your algorithm. So you should have thought of your test up here, and then what you do down here in step 5, you sort of already written step 5. So you figured out as a human, these are the tests, yes it works. Now you have to give those tests to the computer and see if it generates the desired results. And then 6 is debug. The thing about computer science is you're not going to get it right the first time, and that's okay. And if you do get it right the first time, great. But for the most problems, computer scientists, when you're writing code, when you're doing this translation, you don't necessarily get it right the first time. So when you debug, you have to go back and then continually figure out why is my translated solution not working. Now it may be that you didn't translate it right. It may be that you're misusing these pieces over here to get your answer. Or it may be that your original algorithm might not be correct. And so this is the loop that you have to go through to be able to do this. So these are the bases, and we will be covering a balance of these as we go. The pieces I will be presenting a lot in these lectures, especially the early lectures. Once we get enough pieces, then we move into problem solving. Your homework will address a lot of the problem solving. Your test will address both the pieces and the problem solving. So, so that's a general overview, and then we'll move on.